And can you hear me on Zoom now?
Yeah.
Cool. Okay, great. Okay, I think it was just set to the wrong microphone. Okay, great. We've solved the Zoom audio problem, I hope. Let me share my screen and bring up the site class. Just a couple of announcements really quickly before we get into the lecture. Everyone probably already saw or maybe already figured it was the case that Tuesday, or next Tuesday, next week, is a reading day, which escaped me somehow. There is no class on Tuesday, so everything was scheduled got shifted down a day. I accidentally shifted the homework to due date with the schedule down to the next day in class, which I didn't need to do on purpose, but someone had caught it, and so I feel like I can't undo it. So we've got an accidental homework extension. So yeah, the homework 2 is now due on Tuesday, a week and a half from now, 10th of October. There is a caveat. Oh yeah, the other thing is next week, you'll have our office hours as regular scheduled. So Amon, I think it's on Mondays and on Wednesdays. That's still the case even for the reading days. So if you need help with homework 2, and then I'll be available after class today or next Thursday for help as well. But yeah, so the caveat for the extension, the accidental extension, is that this week, Amon and I both have to attend the same conference, MACI conference. And so this week we are not here. We will have lectures recorded. I think Amon's turn. Once we get to that week, I've got the next to today and next week's lecture, and then Amon's coming back, but he will record lectures, although maybe we'll change who's doing what. But right now the plan is that it's Amon, but the important part is don't come to class. You can come here and hang out for an hour, 15 minutes, and we'll be here. But you get on to Canvas and check the lectures and watch them next, 2 weeks from now. But yeah, so we won't be here. So the homework extension, you're on your own, but you maybe want to pretend like it's really due when it was due, because you did get help up until then. But next week, it'll be very difficult to get help. You can probably get us by Piazza, but we'll again be at a conference, so we'll be kind of busy and maybe slow to respond to Piazza questions. So just keep that in mind. I'll send an announcement or remind everybody next week, since everyone will forget after taking a break for reading days. So anyway, yeah, that's the plan. Any questions on that schedule switcheroo? Okay. Let me just tell you what our plan is for today. Amon has done the statistics on manifolds, the mean and principal geodesic analysis last week and last time, Tuesday. And the goal today is I'm going to pick up where Amon left off on principal geodesic analysis, just say a few more words about it and give a sort of boil it down to how you actually compute it in practice, because you have to do this, of course, in homework 2. Amon mentioned it at the end, but he had a shorter time after he covered all the math. I'll try to cover a little more practical computational aspects of how to do it. So we'll just look at the slides there briefly. I also want to point out that this book chapter, you can take a look at. It has more detail even than what's in the slides or what we cover in lecture about how all these things work. Just for reference on how to do things. The next thing, today's main topic, is we're switching from what we've been calling known manifold analysis. So known manifold, like I know I'm on a sphere, or I know I'm on Kendall shape space, so I know how to compute geodesics on that space, to learning the manifold that your data lives on. So remember, again, our mental picture to have in mind all semester is way back in the very first lecture, had this slide with a picture of a manifold, and all of your data lives on this lower dimensional manifold, sort of sitting there in your data space. And now the idea is that we don't know that manifold, and we'd like to learn it. And so this is the general topic of what's called manifold learning, and it's a pretty old topic as far as machine learning topics go. It dates back to roughly, let's say 2000. Although you could say that PCA is manifold learning, it's just the manifold is always a lower dimensional hyperplane. So it's always a subspace, a linear subspace you're learning. Whereas we are more interested in manifold learning of learning nonlinear subspaces that our data lives on. So that sort of came about in early 2000. So it's about 20 some years old, which in machine learning is like the Stone Ages. So we'll talk about some basic ideas there. The references, just to kind of orient everybody, this first one is a relatively old review article of manifold learning, but it's very nicely written to kind of boil it down to some simple principles that we're going to kind of cover here. And see how first multidimensional scaling, MDS, and then what's called isomap works. So yeah, so you can read this. It's it's 17 pages, but you can read it pretty quickly because you kind of just skim through these algorithms. We'll be covering like I said, multidimensional scaling, really the classical version of multidimensional scaling, MDS, then isomap, which is the next algorithm here, locally linear embeddings. And I think, depending on how much time we have, because I don't want to, have this bleed over into the next week after next week, we might at least briefly cover the basic ideas for plotting eigenmaps. So that's kind of the goal here. Okay. Let's see. Yeah, the next paper on here is the original isomap paper. That's what that is. And you can kind of get a picture here. Maybe I'll just kind of point out, just to give you a sense of their result here, some results here, just to give a kind of start at the end, and then we'll back up and go through how they got to this. So this is kind of one of their famous results in this paper. Those of you that have maybe done generative models like autoencoders, variational autoencoders, I should say, or generative adversarial networks, you can think of those models as manifold learning. We're going to cover those models. In fact, some of the recorded lectures, if we stay on schedule, will be about variational autoencoders. And so you can think of those as manifold learning, the more modern version of manifold learning, but the principle is still the same. Maybe I'll draw a picture. I have an eraser. Oh, I need to make sure the camera follows me. Sorry, 1 minute. It's like I have to remember how to give a lecture when we take returns, and it take a break for a while and forget how to set everything up for a minute. Hang on, that's not what I want to do. Zone. There we go. Okay, so yeah, so the picture, and it's kind of, again, things we talked about in the first week or so of class, is that our data lives on this nonlinear manifold. I'm just going to draw some points to represent data living on this nonlinear manifold M. We don't know that manifold now. And what we want to do is we want to find a mapping that maps this manifold down to a coordinate chart. You can think of as in the terms that we've talked about with manifold. You can think of what manifold learning is doing is mapping my data down to a coordinate chart, and at least maybe I don't represent the entire manifold, but I represent at least some coverage where I have coordinates here that map down to coordinates in my coordinate chart. And I should mention that depending on how we're thinking of things, I could be thinking of, I want the map going this way, or I want the map going from the coordinate chart back to my data. If I want a generative model, like we're going to talk about later, I'm really trying to find a representation space, what is typically known as a latent space in machine learning. And I want a arrow or a mapping, typically a neural network these days, to map me back to my data space, so that if I generate data at random values in this vector space down here, it will map them to realistic looking data up here. Manifold learning from back in 2000 with isomap kind of stuff we're talking about. The idea was to go the other direction, where I have a representation, original representation of my data, and I want to map it to some, again, latent representation where I can more easily understand sort of the factors that go into my data. The one thing to consider here is PCA is basically this also. It's just like I said, these mappings are just really affine mappings. They're linear mappings plus a translation to the mean of your data, right? So if I do PCA, the picture is you have Euclidean space, and then you map it to some affine subspace of your data space. And usually this is lower dimensional than your original data space, and I want to find some dimensionality reduction that best captures my data. And PCA, because it's a nice fine mapping, we know how to go one way or the other. You can take your data, project it down to the principal components, or you can start with principal components. And we also know the distribution there is modeled as the Gaussian in the latent space, if you will, in the principal component space, and I can just do the mapping back through the eigenvectors that Aman mentioned to go back to my original data space to sort of generate random data. So the PCA, you can really think of as a generative model, because I have a Gaussian model for how data is generated. It's not a very flexible generative model, again, because I can only do these affine subspaces. Okay, so yeah, so you can think of manifold learning as sort of a natural evolution of PCA, and then you can think of modern and generative models like GANs, VAEs, to some extent maybe diffusion models or another, and lots of other models I should mention, a natural evolution from manifold learning to modern day deep learning approaches. So yeah, so coming back to the isomap paper that we will probably not quite get to. I think we'll just get to MDS today, and just maybe MDS is like the main ingredient of isomap, so it's kind of a step to get there. But just to show you an example, this is from their paper, and the data they had were sort of these computer graphics generations of a statue head that was rotating, and I believe. Oh yeah, this one I think there was lighting direction. Yeah, that's right. So there's really 3 degrees of freedom. There was the head can go up and down, tilt, and then pan, left and right, pose, and then these little bars are the 3rd dimension, because you can't really visualize 3 dimensions on the paper here. So they have a bar about where the lighting directions, the light can move, I think left, right, kind of thing. So the idea is that if you map your data, which now is an image, so it's in this high dimensional vector space, down to this low dimensional latent space, you would like it to be the case that you kind of capture those intrinsic dimensions. Those 3 intrinsic dimensions are somehow naturally learned from your model. And so, yeah, so you can kind of see that the 2 dimensions they have here look like the left-right pose, and you go up and down in this sort of latent chart, it's more like it's like an up-down pose, and then the 3rd dimension we can't see coming out of the board here, but has this little slider to show is where the light's coming from in the face. And they have another example where they take handwritten characters. I believe this was not MNIST. You're probably familiar with MNIST. I don't remember, but this may have been pre-MNIST, but maybe this, no, it is MNIST. Okay, so this was MNIST. And this looks like it's only twos. And so they learned a manifold of what does a two look like. And let's see, what do they call the dimensions here? Here you have to get a little more creative, because what are the degrees of freedom in writing a two? It's not as clear, but the idea here is that they're saying the going up and down is the top arch articulation. So down here you get more loopy, curly Q kind of top arches, and up here they're more flat. And here they're saying left, right looks like the bottom arch. So if you go over here, you get loop-de-loops, if you will, on the bottom part, and over here you get much more straight kind of bottom arches. And again, this is a little bit more fuzzy, you know, deciphering what's going on in the learned dimensions, the learned degrees of freedom here. One last point I'll make here is that in your homework, you're going to be doing the triangle example in Kindle shape space, and so you're doing something that's kind of not this and not that either, but it's in the same sort of camera. It's in the same kind of realm of things. So you're doing a kind of a third thing in the middle here, which is you're doing PGA, and the PGA maps you up to this will be a known manifold. Now you didn't have to learn this manifold. That manifold is Kindle shape space. So I'll just write M is equal to remember CP K for some K value of K, and what you're doing is you're getting these some kind of vectors that the bases here, the eigenvectors, if you will, correspond to eigengeodesics, we can call it here, and they're centered at the mean, the Crochet mean, mu, and moving along these geodesics. So moving in the latent space, the principal component space, if you will move you along geodesics, these principal geodesics. That's the PGA is principal geodesics, and you'll get but the point I want to make here is that what you're seeing here, very similar. You can do this in PCA, you can also do this in PGA, is I can also kind of plot what are the changes that are happening along these principal modes, these principal directions of best explaining my data. And so if you have a shape space and you have a data set, a set of shapes, and you move along, you compute the principal geodesic analysis. First of all, I can plot the shape that is mu. That's not a real data point. It's really a data point I estimate is the mean point. It's not in my data set, but it looks like a real shape in my data set. It should look like an average shape in my data set. And then if I were to move along these geodesics, I should see a deformation of shape, because this is a continuous path through shape space. So every point is a shape. So if I just move along this geodesic back and forth, I should see a shape deformation. You can plot this like a little strip, or you can actually do a movie, whatever. And that is, in a sense, a representation of the maximum mode or variance dimension in my data. Actually, maybe I still have, sorry, I didn't plan this, but I think I still have the video I showed. Let me just check. Yes, okay, good. Let me shoot. Stupid Windows. Need to load it with right media player. So just there's a thing we already saw, but now you have the context for what this actually is. This example, the contrast on the board here in person, or it looks kind of low, but this is an example of the first principal geodesic. These are 3D shapes. You guys are doing 2D shapes, right? Or Kindle shape space. These are three-dimensional shapes of kidneys, like, you know, in your abdomen area. This is learned on the data set of 50 people's kidneys. And the reason it's just 2 kidneys is because I'm just making it so you can see the side and the front at the same time. What's going on? It's the same motor variation, both animations here. So this is the kind of thing you get from the principal geodesic analysis is understanding what are the main modes of variation in your data set. Because we know that these shape spaces are very high dimensional. There's lots of dimensions you can move in. So what these are sort of explanatory dimensions, dimensions that have the maximal variance, they best fit your data. If you could only pick one dimension in the whole data set, in the whole high dimensional space you're in, this is the dimension that most looks like your data. That's one way to say it, okay? And so if I were a doctor interpreting this, let's say, I would say, okay, in this data set, it seems that if I look at just the shape variability of people's kidneys, some people have tall, more skinny kidneys, and some people have, fatter, shorter kind of kidneys. So that's kind of the main biological variability we see in kidneys is the takeaway of this animation. Okay, so that's just a little bit more about what you should expect as the outputs, if you will, of your final homework task here. I think in the homework you are, let me go back. The homework, you're doing triangles, and I forgot if I gave you, did I give you corpus callosums? I believe it was corpus callosums. Let's see. Yes, corpus callosums. I forgot. I couldn't remember because I have a few different data sets that I give sometimes. Yeah, so corpus callosums are just a 2D kind of cross section through your brain. In fact, let me. I probably should put a picture of the homework just to give people a sense, but we can do a really quick trivia facts about corpus callosum, just to show you what the shapes look like. So the corpus callosum is, if you take a person's brain, you've got two hemispheres, left and right, and then there's this band here of axons. Those are the kind of the cabling of your brain, if you will, connecting that left to right hemisphere. And if I were to, again, slice the brain down the middle between the two hemispheres, I would get something like this. This is like looking at the inside of the brain of one of the hemispheres. And that cross section of this bundle of cables is the corpus callosum. It's this shape here. And so if you are doing homework number 2, or sorry, yeah, and number 2 and homework number 2, you should see when you plot shapes, you should see something that looks like that type of shape. So it'll look like, all the shapes should look something like that. And these are real corpora callosa. I can't remember the plural, something like that. There, it's some Latin version of plurals there, and you should be able to see this. And when you do the principal geodesic analysis, well, first of all, you should, when you get a Fréchet mean, you should plot that, and it should look like a corpus callosum. And then when you move along these principal components, like I said, you should see some deformation, and that'll tell you kind of what's the variability in this data set of different people's corpora callosa. Okay. Any questions? Okay, so yeah, really quickly, I would like to just go through a couple points on the slides here just to help with this works. To help with the homework. I think the data matrix, yada, yada, is all very clear. And you can obviously go through this stuff at a slower pace. And yeah, this was the thing. Yeah, okay, let me back up to here, actually. So the first thing is, how do you compute principal component analysis in Euclidean space when you just do a principal component analysis? And the idea is that you're going to take, I do need to get my notation straight, so let me back up here for everybody. What you're going to do, I'm going to use the pointer here, is you're going to take your data matrix, and here the data matrix, each row is a data point, so the columns are a different dimension. So if I have d-dimensional space, I'm at d columns, and I have n data points, that's n rows. And the mean of the data just looks like, take the mean of all the rows, and you get a mean row, if you will, a mean data point. So when I've got a dot here, that means the mean over the j index, sorry, No, that means keep all the J indices. And I'm taking the mean over the I index. Yes. I get my I's and J's and rows and columns. Mixed up sometimes. But yeah, this would be like a mean row. It's a vector of D dimensions, like a row vector of D dimensions. Okay. And then just like we typically would do, we're going to subtract the mean from our data. So this is our mean center data. So that this was the notation I needed to make sure everybody's got is this tilde means mean centered data matrix. So X tilde is the whole n by D matrix, but every row has had the mean subtracted from it. And now, as we know, I can get a covariance matrix just by this equation, which in matrix multiplication just looks like this. Okay, that's the covariance matrix. And most of you probably are aware that there's this is a biased version of the covariance matrix, right? If I want the unbiased version, I do a n-1 in the denominator. This is the maximum likelihood estimate of a Gaussian, but it's not the unbiased estimate. The unbiased estimate would have an n-1 down there. So anyway, there's that little caveat there. Okay. And this covariance matrix, the ijth entry of it is just the statistical or the sample estimate covariance between two dimensions, the ith dimension and the jth dimension in your data is the sample covariance between dimensions, if you will. And of course, we know that this equation is symmetric in ij, so the covariance matrix is symmetric. The covariance matrix is also positive semi-definite, meaning all the eigenvalues are non-negative. You can have 0 eigenvalues if your data lives in a lower dimensional subspace than D. But if it fills up all the dimensions in your D-dimensional space, it'll be positive definite. It'll be all positive eigenvalues, but you can't get negative eigenvalues in the covariance matrix. Okay, yeah, that's kind of what this all says: positive semi-definite. And yeah, so the key is to Aman did a great job talking about the mathematical properties of how you map. The PCA is really an optimization problem that maximizes variance of your projected data. It also minimizes the residual variance or of the errors, the residuals that you're leaving out when you project to a lower dimension. So you can think of the least squares problem. It minimizes the residual sum squared errors. So it's the best fit or the least squares fit, again, of a fine subspace to your data. And yeah, so the point here is that to get the principal component analysis, you do a eigen decomposition. So I'll just skip down here. That was just about what's an eigen decomposition. And so I take my sample covariance matrix. Let's see if camera follows me. I take my sample covariance matrix and I just do the eigen decomposition as a vectors, eigenvector matrix, D by D eigenvector matrix. Lambda are the diagonal matrix of the eigenvalues, so the lambda k are the eigenvalues. And each of these eigen vectors, Vk, are those dimensions of maximal variance. If I sort them with respect to the decreasing eigenvalues, so V1 would be the highest, lambda 1 would be the largest eigenvalue, and V1 would be the eigenvector associated with it, then the lambda k are those variances in those dimensions, as we know if you've done PCA before. So just in the picture up here, again with my pointer, if I had a data cloud in 2D that looked like this, the sort of the covariance would be fit like these ellipsoids, if you will, or ellipses, if you will, and the big axis of the ellipse is the maximal variance. That's lambda 1 V1 direction. The VKs, just to be clear, are unit vectors and they're orthogonal to each other, so orthonormal basis. And then you can think of the scaling as the lambda k's, how much variance, how much spread is there in my data for dimensions. Okay, so yeah, that's the PCA algorithm. I just compute covariance, I take eigenanalysis, and then I've got eigenvectors, those are principal directions, and eigenvalues, those are the variances in those directions. Yeah, this is the point that if the least squares fit. So Aman presented everything in terms of maximizing variance. it's equivalent, so he had an arg max of subspaces, but it's equivalent to arg min residuals that you're leaving out. So if my data, if this is my k-dimensional PCA, if my data is up here and I project it down to this k subspace, and I did that for all the data points and summed up these distances, these residuals, then that's being minimized with PCA. Okay. And it turns out the reason that's true is because maximizing variance, the variance is just this direction, okay, from the mean, and the error or residual distance is this direction. This is a right angle because this is an orthogonal projection. So the total variance is sort of the hypotenuse of this right triangle. And I know that if I have a right triangle, call this A, B, and C, I know from Pythagorean theorem, A squared plus B squared equals C squared. C squared is fixed. It's just how far my data is from the mean. If I want to maximize A squared, I'm simultaneously minimizing B squared just because of Pythagorean theorem. Okay, so that is why this has this dual meaning of maximizing variance or minimizing error, squared error. In principal geodesic analysis, if I say I want to maximize variance, it's not the same as minimizing residual error. So I could have to pick one or the other as either a min problem or a max problem, and they're not equivalent because there is no Pythagorean theorem for general nonlinear spaces, Riemannian manifolds. And you can kind of see this with the sphere. If you take, say, the equator and take a quadrant or octant, I guess, of the sphere. So this is a triangle I'm drawing, 3 sides here. And if you imagine this is kind of straight down the kind of the YZ plane, if you will. This is cutting through the XY plane, and this will cut through the ZX plane. So like a 3 orthogonal planes here. Then all of these are right triangles, first of all. You remember from Euclidean trigonometry, right? A triangle in Euclidean plane adds up, that angles add up to 180, right? Here, you've got 90 plus 90 plus 90, you've got a 270 angles is the first thing. Then the other thing is each of these sides is pi over 2. Okay, so pi over 2 squared plus pi over 2 squared is, of course, not pi over 2 squared. So it breaks the Pythagorean theorem, and you can play around. You can get all sorts of different combinations of this not coming out to the planar case. There is, by the way, a version of this Pythagorean theorem on a sphere. It's just a different equation. It's not a squared plus b squared equals c squared. It has like cosines in it and things like that. So anyway, yeah, so the bottom line here is that with principal geodesic analysis, if I go with maximizing variance and I did that optimization with a set of data, I would get one solution. If I change my formulation to do this minimizing residual square distance, I would get a slightly different solution. Depending on how spread out my data is, the closer it is together, the closer those two solutions, because it will look somewhat linear, those solutions will be closer to each other, but they can be different. Okay, and so to skip all this, come to the principal geodesic analysis. Yeah, that's principal component analysis. As Aman talked about, this recursive, like adding one dimension. You kind of think about adding 0 dimension as I add a point, the mean point. That's the best approximation with 0 dimensions of my data. With 1 dimension, that's the best approximation of my data. 2 dimensions, I span, I add another dimensions. Same thing with PGAs. I'm going to compute a mean. The Frechet mean is at least the least squares, best approximation of my data. Then 1 dimension is the first principal geodesic, and I can kind of span higher and higher dimensions by adding more geodesics at a time. And so this was what Aman covered. No, sorry, actually, this is, again, the flip version from what Aman covered, the arg max over variance, but this is the arg min over residuals. I'm not going to go over all that math again. What I did want to do is go over the how to compute it. As you could get a sense here in Tuesday's lecture, when this was argmax, but same kind of point is this was the same. You still are trying to find this subspace that the geodesics span, this geodesic subspace H, which are like geodesics emanating from you in the eigenvector or the PGA dimensions that you're finding these dimensions V's, and spanning kind of all the geodesics that flow out of that mean with those this kind of linear subspace in the tangent space. And the problem is that you then have to project your data on the manifold to the closest point of that subspace. And that is, for most manifolds, an optimization problem itself. So pi projection is you have to find that point, optimize it. And then you have to optimize the whole thing here. So it's like an optimization within an optimization. This becomes a really difficult thing to solve exactly. It can be done. If you're interested, Google the phrase exact principal geodesic analysis, and there is a paper on how to do that. So yeah, so you can do this, but more often than not, the following approximation works really well, and this is what you should do in the homework. Unless you want to really get crazy and solve the exact PGA, then the approximation is the following. You compute the Frechet mean. You then compute the log map of all of your data, the data of the yi's, from the mean mu to the yi's. And so now I've got the tangent vectors that represent the geodesic segments from mu to yi. And they're all in the tangent space centered at mu. And so now I've got, you can think of this as a vectorized form of my data. And now I can just compute a covariance matrix of that vectorized data in the tangent space. And so now I've got the n-1. For some reason, I've switched conventions and put a unbiased estimate of the covariance down here. So capital S is my sample covariance in the tangent space. And I very simply just now do what I would have done with PCA. I just do an eigenanalysis. I get the eigenvectors and the eigenvalues of this sample covariance. Okay. And so let me actually add, I don't know if there's another, this next, yeah, this is the last slide, that's what I thought. So there's one more final point to say about that. Let me kind of add to this picture of PGA here, just in case anything else. So yeah, these are my, down here, I can think of these directions are my tangent space. Let's say this is my, I would draw it here, but just to make things clean. This is my tangent space here centered at mu. And so this is V1, V2, and so on if I can draw more dimensions. Again, if I move along these dimensions, then I'm gonna, with the exponential map, be moving along this principal geodesic. And so how would I do that? Let's say I call this principal geodesic gamma 1 for the first principal geodesic. Gamma 1 of t, I can write as just an exponential map starting at the mean, and t times v1. Okay, and so t goes from minus something to something. I'm just down in the tangent space, I'm moving back and forth along this line that v1 spans. But if I then take the exponential map, that is giving me a parameterization of the geodesic. So this is how you can kind of plot these shapes along the principal geodesics. One little thing to add to this is that, of course, how far you go around these geodesics is determined by how much the data is stretched out of that dimension. And so you really want to stay kind of in units of standard deviations of your data. So you can put in a square root of lambda 1 in this case. Because if lambda 1 is the variance, like a sigma square, oops, sorry, board moved. If lambda 1 is like a variance, then square root is like standard deviation. So t is units of how many standard deviations do I want to move in my data set. And things are down the kind of the way to think of this is I'm again trying to fit something like a Gaussian, non-linearized Gaussian to my data from the mean. And so there's the usual rule of thumb that you go 1, 2, 3 standard deviations roughly. It gives you like 99% of your data. So you can kind of get an idea of how far, plus or minus, you want to go in terms of standard deviations. Okay, any questions about how to do the approximate principal geodesic analysis? Thought this was going to be like a 15-minute summary, but we're over halfway through the class. That's okay. Any questions? Yeah.
For 2 is that log base of the Freshet mean that we?
Yeah, I think my subscript, I didn't do a subscript. That should be a log subscript mu yi. Yeah. So thanks. Yeah, by the way, I wanted to I can't remember if I made this point way back when we were talking about exponential log maps. To get a better kind of intuition for what's going on here, what we're doing is again, you think of my yi's, my data are living here on the manifold, and then the log map puts them here in the tangent space, right? And the way to think of this is from the mean, the little geodesic segment that goes to a yi here is going to be converted to a straight line in the tangent space that goes to my log of the yi. And the key point here that makes all of this work nicely is that these geodesic segments have the same length as these linear segments. So I can't preserve all the distances pairwise between any 2 points in my data set and map them to a linear space. So if you think about a sphere, I can't flatten a sphere and not stretch some distances. Like you probably know about like maps, right? Like I can't take a map of the Earth and make it flat like the globe and not like stretch Greenland or shrink something else, right? I have to stretch distances to flatten a sphere or even like a hemisphere. Okay, so there's no way to preserve all the distances, but we can preserve distances to the mean at least. And that's the log exponential map. They go back and forth, preserving at least the radial dimension distances. Okay, so to the best we can possibly, we can preserve those distances. And then the way to think about it is distance is variance. The variance, as Aman told us, the variance of my data is equal to, again, I can do a n or n minus 1 here. But it's the expected value of distance from the mean to my data squared. Okay. And these distances, mu to data, are preserved again through this log map. And so variance along this linear dimension is the same as variance along this geodesic dimension in that sense, that you're at least getting the radial variances or distances preserved. And so, yeah, so the thing I like to have a mental picture of when I'm thinking about exponential log mapping, again, just our favorite 2D manifold S2, the sphere embedded in R3. And if you can imagine taking just any vector that's tangent to the North Pole, and think of this as a piece of string that a little segment of string that you stretched out. And then just let this part of the string just fall, and it will wrap around the sphere to some point. That's the exponential map. So it's just wrapping, assume that this sphere is nicely aligned. The axis is going to align with gravity, if you will, and this just falls along that dimension. That's just kind of the z dimension only, and it will wrap around to the geodesic segment, the great arc or great circle that is geodesic in that direction. And then the log map just says, take your tip of your string and unroll it again straight up against gravity's direction, and straighten it out till it's tangent. And that's the log map. And of course, the string is rigid in this dimension. You can't stretch the string, let's say. It keeps its length as it drops or gets pulled back up. And that really is the exponential map, log map for the sphere. Okay, great. Any other questions? Okay, so now to start today's lecture with 25 minutes lecture class. We're going to talk about multidimensional scaling. And I can do this quickly because it turns out, I'll give you the punchline of the lecture at the beginning here, that multidimensional scaling is just principal component analysis. So we've actually already done multidimensional scaling, but you don't realize it. And so I will attempt to make that connection in 25 minutes here. Let me stop sharing and turn off the screen. Always resisting turn off for some reason. Have to like it's fine. This LCD panel. Yeah, like right here. No. Oh, there we go. No, it's just there's a two. I always forget. Okay. Yeah. Okay. Good. So multidimensional scaling. I should back myself up a little bit and say that multidimensional scaling, the classical version of multidimensional scaling, is the same as PCA. It actually can do more exotic things than that, but the classical version that we'll talk about today is really just principal component analysis. But how many people here have used like multidimensional scaling before, or anyone? Yeah, it's not as common. How many people have used PCA or seen it in a class or something to that effect? Okay, so just a couple people. So, okay. Right, so yeah, multidimensional scaling. I'll give kind of the goal here. So the goal, or the setup, I should probably call it, is I start with pairwise distances in my data. D, and I'm going to write this as a matrix. Dij is equal to the distance between the ith data point and the jth data point. Okay, so I'm assuming that my xi's, xj's, whatever we're calling them, these are my data, that they have a metric. They live in a metric space, and that's D gives me the distance between two data points. And I'm just going to put that in a big n by if n of these xi's, then I'm going to put that in an n by n matrix. So the ijth entry of this matrix is just the distance between those 2 points. And of course, again, this is a symmetric matrix because if I flip ij, the distance from ij to ji is the same. And so we have that. And what I'm going to do here, I'll start out with I'll really work with the square distance matrix. So I'll just take every entry of this matrix and just square the number in there. Okay, just to do the math here. But yeah, so the setup to this is I know the distances between my data and nothing necessarily else. Okay, so I've given you, I could even throw my data away now. So say my data are super high dimensional. Or you know, hard to work with for whatever reason, I might want to just toss the data at some point and say I just know the distances, the relationships between how similar different data points are to each other, and that's all I need to work with here. And now the goal, I should say, this is the setup. The goal is to reconstruct. I might just really call it construct because it's coordinates I'll call them xi tildes. So they're like fake xi's because I've thrown away the real xi's. Let's say I've only been given this distance matrix. I'm going to reconstruct coordinates xi tildes which are in some Euclidean space Rm. Let me just, yeah, here I don't actually even care. I don't even know maybe what xi's came from, or did they come from a d-dimensional, n-dimensional, some dimensional space. I don't know. I don't even know if they're Euclidean, maybe. And I'm going to have some dimensionality that I'm going to want to represent these data in. So my goal is to visualize my data, like I'm doing some exploratory data analysis. I might just pick M to be 2 because that's how many I can plot in 2D, or I might make it 3 if I want to interact with kind of 3D plot of my data. And I'm going to come with these fake data points or xi tildes such that the Euclidean distance of these fake data is as close as possible to the distances I was given. So the xi tildes minus xj tildes, these distances, or I'll call it the square distances because that's what we did here, is approximately, or as that's what my squiggles mean, as close as I can make it to the distances in my original data set. Okay. And when I said NDS is just PCA, again, a very specific application, if your data came from a Euclidean space and the distances you were using were Euclidean, so let's say again, I have like something like images, it's a high dimensional Euclidean space, and I just compute the distances between those images, and then I want to somehow wrap my mind around what these images are doing. In data space, I could project that into a lower dimensional latent space, if you will, by solving the MDS problem. But we know that that's exactly what PCA solves. So it turns out that if these distances are Euclidean distances, meaning they already look like this, but just in some higher dimensional space, and maybe I'm going to put it in, this would just be like a principal component analysis and picking the first M principal directions to project into. That being said, I can also do multi-dimensional scaling if these distances are not Euclidean. So say I was given points on a sphere, some high dimensional sphere maybe, and I want to do pairwise arc length distances between points, things like this. Okay. One example I'll give just as a, and you can find this example on the web if you just search for this, is you can, for example, take say like major cities in the US or wherever you want. So take Chicago, New York, Los Angeles, Atlanta, what have you. Compute their distances, just, you know, and these would actually be arcs on the globe, right? And then you do NDS in R2, and you'll get a map of the United States. So if you get, you know, you'll get a configuration where those points are now plotted like you would plot them in a 2D map of the US. So, you know, Los Angeles will be over here, Chicago will be here, let's say Charlottesville's here, Miami, you know, New York, and it'll be kind of like my poorly drawn US map. They'll all be in the right configuration in your projection of things here. But you don't need to know anything about the city except how far apart they are from each other. You don't need to know an actual coordinate for the cities or longitude, latitude, or what have you. MDS will build the map for you if you just knew like how long does it take an airplane to fly from point A to point B here. Yeah.
What is xi belong to Rm? Because like is there like a projection to Rm?
Well, yeah, these again are just purely made up coordinates. So MDS makes up these coordinates. Its output will be these XI tildes. You have to pick the M. We're going to talk about that part at the end here, where you give it an M, if you will, and what you're saying is I want my data to be represented in an M-dimensional Euclidean space, and I can pick the M, like I said, either like here I would pick it to be 2, just because I want to plot. I know it's a map. I want to plot it in 2D. You know, that's but if you don't know, you can look at, you know, what we're going to get is eigenvalues. You can look at how many eigenvalues I need to capture how much of variance my data I want and pick that for your M.
So, I mean, like, so xi in the Rm is just basically the same thing as xi.
No. Xi tilde is fake. Xi is real, the real data
Yeah,
points.
but how do we represent? the
Xi, so for instance, here in this example, Xi lives in S2, completely different space, the globe, if you have cities. And the Xi tildes I'm going to plot are going to live in R2. Here are my these are Xi tildes, and they are in R2, completely different spaces.
Yeah, that means that we actually don't know how Xi is being represented.
You don't, I mean, yeah, MDS is going to generate these outputs. I'll show you how it's going to be computed. If you, you know, but yeah, you don't, it just gets made up by the algorithm at this point. And it does it to solve this kind of optimization. It's going to say, I have these distances as inputs. These are the inputs. This is my only input, is the DIJs or DIJ squares. And so MDS is going to say, I'm going to make up these coordinates to minimize the distance, if you will, between the distances or the square distances. Which I should mention in my map example, if you take the United States and you rotate it, the plane here, you don't change the distances. If I flip the plane, I don't change the distances. So MDS has somewhat of an arbitrary kind of orientation, rotation, flipping, if you will, of these fake coordinates. So it's not a unique solution, is my point. That you get, you can rotate things around and get the same optimization answer here. Okay. Okay, so yeah, so how does this work? Let me just give the algorithm, and then I'll kind of come back and give the general intuition for what's going on. And I will wave my hands over some details of the derivation. You can read the paper that I have there for more of the gory detail. It doesn't actually, I have the gory details, but if you, I think, go to Wikipedia, you can get some gory details. Yeah.
What is an application of NDS in image analysis? Is it the mapping from latent space to some fake data points?
So the for our purposes in this class, that the one application I'll say is it is for one step of isomap. So when we do manifold learning, it will see is a step where we will get a latent representation of our data. And so yeah, so this is, I'll come back over here. Notice this is going from the, let's say, you know, if my data does live on a manifold somehow, and maybe it's not the sphere, maybe it's some data manifold, I don't know. I'm going from the data manifold down to a latent representation. So this is the arrow that I showed going from my original data representation, which I, let's say, have a metric in. Okay, this is my original data, and this is my latent space, the Xi tilde that it's going to produce. Okay, and so we're going to see with isomap that you basically have a little bit more steps added to MDS to make this general manifold learning problem. So yeah, so that's the main application of MDS but it's also very useful in I think exploratory data analysis. Like if I have data and I want just a really quick and dirty way of looking at relationships, maybe clustering of my data, is like, are there things clustered in my data set? I can visualize very quickly, and maybe I have like distances that are non-trivial, they're non-Euclidean up to my data. I can visualize kind of relationships in my data because I'm preserving these distance relationships as best as I can into a flat space that I can visualize. So even if you don't think about manifolds and so forth, then you can still visualize relationships between your data points with MDS. So one other example is like a lot of times in text, people will come up with metrics of like how similar either words or sentences are to each other. To, you know, like a cosine distance or like the edit distance is even more basic. All those things are valid distances, and you can take text and talk about how far away two words or two sentences are, and you can then like visualize those relationships in you know, with the, again, it's a quick and dirty way, there's more sophisticated ways to do all this, but yeah, there's lots of examples, it's not just Euclidean space, or just images, there's lots of different data types. I can think of ways to talk about how similar or distant, 2 points in my data set are, and so those would be applicable to kind of get us a handle on what are some properties of my data. Okay, so yeah, let me do the algorithm here. And we're starting to look like I may not completely finish my explanation for why this is PCA in the classical case. So let's do the algorithm. See how far we get. NDS algorithm. Number one is, yeah, I compute or get somehow my D squared matrix. That's the D squared is the, if I put all those IJ entries into a matrix. Okay, so get or compute D squared. And number two, I compute a matrix B, which equals minus 1/2. I'll explain hopefully here in a minute. D squared J D squared J. By the way, a little bit confusing. D squared does not mean matrix D times matrix D, right? It's square each entry of the matrix D. So it's kind of abusive notation to call it D squared because that looks like D times D and it's matrix multiplication, but it's element-wise multiplication. So just keep that in mind. Here, the J matrix is the centering matrix, called centering matrix. It's I, the identity matrix. And remember, D now is n by n, where n is the number of data points. Okay. And so I'm going to have 1 over n, the unit vector 1 times itself transpose. This is, I'll put a little subscript n. This means a vector ball 1, an n-dimensional vector ball 1s. So 1, 1 transpose is an n by n matrix of all 1s. Is another way of saying this. Okay. And I multiply that by 1 over n. Now, what does this matrix do? If you think about a row of this matrix, the J matrix, it looks like minus 1 over n in all the entries, except for on the diagonal. Let's say this is the diagonal element. It's 1 minus 1 over n, right? And every other entry is minus 1 over n. Now, if I take a vector and multiply by this matrix, when it hits this row, like I have a vector over here, a column vector, and I hit this row, it's going to sum up every element of this row, or sorry, of that vector, multiplied by minus n. And except for the diagonal element, it's going to subtract the mean of everything else. Okay, so what it's doing is it's taking a column vector and subtracting out the mean there. And so if I multiply it by a matrix on the J onto the right here, each column is being centered, its mean is being subtracted from it. Okay. And now if I multiply it on the right, J on the right, I'm taking the mean of the rows. Okay. So this is called a double centering. This is a standard trick in statistics. People do this all the time. If you wanted to get like in PCA, the X matrix, you wanted to subtract the mean of the rows, right? You would just multiply by this centering matrix, and that does it for you. Now for the D squared, I'm going to center the rows and the column. I'm going to do it on both sides. Subtract the mean of the columns, subtract the mean of the rows. Okay, so that's what that's doing. Let me move over here to get step 3 in. So now I've got this matrix B, which seems kind of mysterious, other than that's the D matrix, the D squared matrix center, and there's this weird minus 1/2 factor there. And now what I'm going to do in step 3 in MDS is I'm going to do an eigenanalysis. Okay, and that's just B equal to V lambda V transpose. So again, eigenvectors and diagonal matrix of eigenvalues. And now I want to get my X tildes, okay, from this information. And so the last step is my matrix of X tildes. And when I say matrix of X tildes, what I mean is I'm going to get each data point as a row of this matrix. So the fake data X tilde, the made up coordinates, each row is going to represent the ith row is going to represent the ith data point, but now in Rm and these made up coordinates. So just to be make sure we get our dimensions straight, this is an n by m matrix. I have n data points, n rows, and each one is in Rm, fake latent space, if you will. Okay. And that matrix looks like, I'm going to call it Vm, and that means the V matrix, just taking the first m column, so the first m eigenvectors. Remember, V is a n by n, n being the number of data points matrix. So if I take the first m columns, I would have to enunciate n and m. Be careful. N by m matrix is what I have when I take the first m columns. Okay, and multiply that on the right by the matrix of the first m eigenvalues square root. Okay, and this is just an m by m diagonal matrix of just the first m eigenvalues that are associated with the first m eigenvectors. Okay, so that's the algorithm. Any questions about how? I mean, each step is pretty straightforward. You could implement this in Python probably right now before this lecture was over, almost. With you know, because we all have all these matrix operations at our fingertips, so this is a very easy algorithm to do. Yeah.
Oh, we get an XM matrix there. Upside down V.
This upside down. Wait, upside. Oh, the lambda. That's the eigenvalue. So you. This is eigenanalysis. So you just call a library that like NumPy Linalg that does eigenanalysis of this V matrix, and you get eigenvector matrix, and you get the lambda eigenvalues. That's a diagonal matrix. I'm going to just take the upper m by m, meaning just the first m of those eigenvalues, and make it a smaller
So like
subset.
there's a library that would do this for us.
Yeah, so this eigenanalysis, in fact, in your homework, the PCA, you should do take a library to do the eigenanalysis. You don't want to reinvent the implementation of an eigenanalysis. Yeah, so just call, I'll probably get it wrong, but it's like NumPy has a linalg packet part of it, and there's like an I want to say it's IH because it's IH is like if you have a symmetric matrix, the H means Hermitian, so it's a symmetric. So yeah, so you just do a library call.
I mean, like it returns like a tuple, that's the triple value.
It'll just return the V and the lambda. That's all that you need. Yeah, the V will be a matrix, and lambda usually is just a single vector because it's just the diagonal that are interested in. Yeah. Okay. Yeah, and so my punchline that I gave at the beginning that this is just PCA is, again, if your D squared is Euclidean distances, then the V and the lambda you get is the same thing as if you did have the original XIs and you computed a PCA. You would get the same V principal dimension, principal vectors, if you will, and the same lambdas, which are the principal component or the principal variances, if you will. Okay, and if I did the projection of my data onto m dimensions, the first m principal components, this is what the PCA would do to get that. No, sorry, I have to back up a second. It's in a slightly different space. It's actually what's called dual PCA. I forgot to. I need to make this distinction. Is that the V's are, remember, in NDS n by n, in PCA they're d by d, where d is the columns. And so the difference is dual PCA is that if I have an original data matrix X, okay, I can take X transpose, and that gives me roughly my covariance if I center my X's. MDS is doing an eigenanalysis you can think of as X transpose X. And so that's the dual is X versus X transpose, which dimension you call the rows and which one you call the columns. But they are in the end actually equivalent. You can show that the lambdas come out the same, the eigenvalues come out exactly the same. There's a conversion to go from V's of this eigenvectors of this to go to eigenvectors of this by multiplying by X or X transpose. You go from the eigenvectors of this guy to the eigenvectors of this. And so that's the duality of this would be called dual PCA is what we're doing in MDS if you have Euclidean values. But more generally, like I said, MDS can take any kinds of distances, not just Euclidean distances. So that's where it's a little bit more interesting is to do non-Euclidean distances, because if you have Euclidean distances, you basically just get PCA. The only difference is that you can start with just pairwise distances and not the raw XI values if you had that instead. Okay, so we're out of time. So on 1 week from today, Thursday, we'll pick back up on the MDS algorithm. There's one more thing I want to say about it, and then we'll see how MDS is used to give us this isomap embedding in Euclidean space. Yeah.
Guarantee that the B has no negative eigenvalue.
Yes, that's what the point I was going to make on next Thursday. I'll make it really quickly now, but I'll say it again on next Thursday, is that when D is non-Euclidean distances, you can get negative eigenvalues here. And if you sort from high to low your eigenvalues, you have to stop before you get to negative values, or else you can't take a square root. And what that tells you is that first thing it tells you is your distances are non-Euclidean. Because if you have Euclidean distances, this is like a covariance decomposition. Everything's positive or non-negative. And so you can detect whether your distances are Euclidean. That's the first thing MDS can do for you. The second thing it can do is say, when you get to negative values, or really when you get to zero eigenvalues, you don't go any further. So the best it can do is give you M dimensions where M is the maximum would be however many positive eigenvalues you have. So you already have a max of how many dimensions you really can represent your data Euclidean if you will. Yeah, so that's a great question. Yeah, that's what you can do with non-Euclidean distances there. Yeah. Okay. Everybody have questions? All right, great. See you everybody in a week.